So this week we are going to continue on with equilibrium involving acids and bases and focus on calculations. So we're going to focus on equilibrium constant calculations involving acids and bases. Now some things we do need to remember are on this diagram. So when we see some of these questions, sometimes we might be given pH or we might be given pOH. However, when we're using equilibrium expressions, we need hydronium ion concentration or hydroxide ion concentration. So remember that to go back and forth, it's a logarithmic scale. So if I have pH, 10 to the negative pH is my hydronium ion concentration. If I have my hydronium ion concentration, I need to take the negative log of that to get my pH. So it doesn't change anything, but this is important for how we communicate our answers and how information is given to us this week. So remember that K expressions are products over reactants. Well, Ka is the acid ionization constant. So the A just is specific towards acids, things that give up protons. And it's still products over reactants. Now, strong acids donate protons very aggressively, like Drake here, making it rain. Protons, 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 or dollar bills. So they make it rain protons. So if they give up a lot of protons, they're going to produce a lot of products. Remember, if Ka is greater than 1, then products are favored. And if Ka is less than 1, then the reactants are favored. So strong acids ionize greater than 99%, produce a lot of products. When we look at our formula sheet, the 6 strong acids that we need to know have Kas that are very large. They don't even give numbers for them because they ionize such a large amount. Those were the calculations that we focused on in Chem 20 because our acid concentration is equal to our hydronium ion concentration. Now in Chem 30, it's different. Now we are dealing with weak acids and weak bases. So these have Kas which are less than 1. So they're weak acids, they ionize less than 50%, which means that we still have a lot of reactants at the end. In order to do calculations for weak acids, we need to use equilibrium expressions. So weak acids, they reach equilibrium. So less than 50% actually goes towards making products. In order to evaluate the pH or the hydronium ion concentration for weak acids, we need to use equilibrium expressions. Now remember, Ka is products over reactants. So my products are the hydronium ion concentration times my anion. In this situation, it's A minus. There's no coefficients, so I don't need any exponents. Divided by my reactants, which is HA, and H2O is not there because it's a liquid. Remember, we don't include liquids or solids in equilibrium expressions. So this is a general equilibrium expression for an acid. My hydronium ion concentration times the anion divided by the acid. Go here. So this is the equilibrium expression. Now, when we do these calculations, we can simplify this expression. Now, what we're going to talk about next is not the equilibrium expression. That's this. This is the equilibrium expression if you're asked for that. However, when we do calculate, now remember that looks different than this. This looks different. This is the equilibrium expression. Now, when we do these calculations, we can use this shortcut because we know that the products are going to change by the same amount, the reactants are going to change by the same amount, and also there are some special cases when it comes to weak acids and weak bases and the amount that they ionize. So when we do these calculations, we have this formula where Ka is equal to my hydronium ion squared divided by my original weak acid concentration. This is a simplified version to make calculations easier. The reason why the hydronium ion is squared is because A minus is pretty much the same thing. So hydronium times A minus is the same as just saying hydronium ion squared. Ka Now this is in your data booklet. In your data booklet, you got 2 pages, or 2 pages of KAs. That's where we can find a lot of that information. The other thing I mentioned is this is the original acid concentration. Now, usually when we do these equilibrium expressions, these are equilibrium concentrations. That's what we've done like with ice charts, and that was the whole point of them. However, there are some rules for weak acids and weak bases which make this okay. For most weak acids, they ionize less than 5%. So they ionize actually a very small amount, goes towards making products, where a majority of them are reactants at the end. Now, because they ionize such a small amount, this change in my original acid concentration, if I were to compare like the initial, okay, so if I were to do an ice chart, the initial concentration would maybe be 0.050. The equilibrium concentration would maybe be 0.0499. Now, those numbers aren't the same, but if we think about significant digits and what we actually know, we can only measure to a certain amount of reliability. And when we round this, according to significant digits, we end up with that 0.050. So that's why this change in that original acid concentration is ignored, because it's usually so small that we don't need to incorporate it. So here's a question. Boric acid is used for waterproofing. So we want to find the pH of a 0.50 mole per liter solution of boric acid, and it gives us the Ka. If the question doesn't give you the Ka, it's in your data booklet. So that's the other place we can look and find these. Now, a common mistake that students will make is they'll just go the negative log of 0.50 moles per liter, because that's what we did in Chem 20, and then that would give us the pH. That's wrong. Don't do it that way in Chem 30. We need to use our formula. So Ka is the hydronium ion squared divided by my original acid concentration, H3BO3. So my Ka times H3BO3, my boric acid will be my hydronium ion squared. And so the square root of Ka times my original acid concentration will be my hydronium ion concentration. So Ka is 5.8 times 10 to the negative 10 times my original concentration of 0.5, and then I square root it. So my hydronium ion concentration is 1.70 times 10 to the negative 5 moles per liter. Now this question asks for the pH. So this is an example of why we need to know those calculations so that we can convert these. So the negative log of my hydronium ion concentration is going to be my pH. So the negative log of my answer, negative log, and then second answer is 4.77. We'll go to 2 decimal places. So there's my pH. Now, one thing to note, if we're dealing with Kas, we're dealing with hydronium ion concentrations. If it asks you for hydroxide ion concentration or something different, and we're using Ka, Ka can only be used with hydronium ion concentrations. That's Ka. Now, similar to dealing with hydronium ion concentrations, strong bases produce a lot of hydroxide ions. In Chem 20, we dealt just exclusively with these ones because those are strong bases that just dissociate like other ionic compounds do. They have Kb's, so now they have base ionization constants that are very large. Now we are going to be dealing again with weak bases. Now weak bases, again, they reach equilibrium, and our Kb is our products over our reactants, and again, water is not going to show up there. Remember, bases are different than acids in that bases accept protons and form hydroxide ions in solution. Base ionization. Now our data booklet gives us Kas, but when we're looking at constant, or when we look at the shortcut for bases, which is the hydroxide ion squared over my original base concentration, I am dealing with Kb. Now that is different than Ka. Our data booklet gives us Kas. It doesn't have a column for Kbs. However, we can find Kb because just like Kw is the hydronium ion concentration times the hydroxide ion concentration, it is also equal to the Ka times the Kb. Kw, remember, is 1.0 times 10 to the negative 14. So our data booklet gives us Kas. If I wanted to find the Kb for any of those entities, I just take my Kw, 1.0 times 10 to the negative 14, and divide by my Ka. That will give me my Kb. So there will be questions where you'll be given the entity and it's in your data booklet. But if we are dealing with hydroxide ion concentrations, we need to be dealing with Kbs. So we need to take our Kw and divide by our Ka. So here we have aniline. Here I want to calculate the base ionization constant. So aniline is this base, C6H5NH2. So in a aqueous solution, it's going to take hydrogens off of water. So I'll have C6H5NH3 plus and leave behind hydroxide ion concentrations. Now the shortcut's the same, although now it's dealing with Kb. So Kb is my hydroxide ion squared divided by my original base concentration, C6H5NH2. Now this question is asking for the Kb. So I need to know my hydroxide ion concentration and my original base concentration. My hydroxide ion concentration can be found here. So this is pH. Now pH can give me my hydronium ion concentration, but I want to find my hydroxide ion concentration. So I'm going to take my pH and then find the pOH. So 14 minus 8.68 means I have a pOH of 5.32, and then 10 to the negative 5.32 will give me my hydroxide ion concentration. Second log button gives me the 10 to the x, negative 5.32. So my hydroxide ion concentration is 4.79 times 10 to the negative 6 moles per liter. Now you remember that that's squared, divided by my original base concentration of 0.054 moles per liter. So I square that top number, divided by 0.054, and I get 4.24 times 10 to the negative 10 as my Kb. So this is a relatively basic question. Again, the ones we need to be careful of are the ones where we're asked to calculate maybe the hydroxide ion concentration or the pH, which would be an extra step. But we're given things in our data booklets which are Kas. So if we're dealing with hydroxide ion concentrations, we're dealing with Kb. If we're dealing with hydronium ion concentrations, we need to be dealing with Ka. If we're doing the negative log of the original concentration, we're doing something wrong because in Chem 30, we're going to be exclusively dealing with weak acids and weak bases.